my name's Logan and welcome back to the lecture hall. For today's Math 2B Single Variable Calculus course lecture video, we are covering section 7.1, Integration by Parts. And so we begin with our product rule for derivatives. What? You'll see why. So we know very well by now that d dx of f of x times g of x is equal to f of x times g prime of x plus g of x times f prime of x. First d last plus last d first. And so now, if we wanted to integrate both sides, what would this look like? Well, we can just integrate, and so in integral notation, we can then rearrange and say, well, this is just the integral of f of x, g prime of x, dx, plus the integral of g of x, f prime of x, dx, is equal to, now, our f of x times g of x. And so, we can actually rearrange this a little further by subtracting this g of x, f prime of x dx over to this side, and we can actually say the integral of f of x, g prime of x dx is going to be equal to f of x, g of x, minus the integral of g of x, f prime of x, dx. And so maybe, why would we even want to do that? Well, if, for example, we had a combination of two functions that we wanted to integrate, and then we're like, okay, we don't know how to do like a u substitution on that or something, well, maybe we have two separate functions, and we can just say, well, one is the function and one is the derivative of that function. Well, then we can make it very easy and we can just go through and solve the integration from what we got with the product rule. Now, this is all great, but this is a lot to write out, and what we can actually do is we can do a u and v substitution, where we take u equal to f of x, and then that would mean du is equal to f prime of x. So let me write that out. So we could take f of x and turn that into u. And then we could take f prime of x, that would be du. And then we could say, well then, dv is going to be equal to g prime of x dx, and then v is going to be equal to g of x. And then this f of x would also be u. So we can write this out and say, well, u is equal to f of x, du is going to be equal to f prime of x dx, and then our dv is going to be equal to g prime of x dx, and our v is just going to be equal to g of x. And so now we can change this formula and say that integration by parts is, well, a lot simpler. It's the integral of u dv is equal to uv minus the integral of v du. And so this is one way we can do it. And so now let's begin with an example. So if we wanted to find the integral of x times sine of x dx, we can do this, but we've never really seen how, and it's a product of two functions. So then we see, okay, if it's a product of two functions, we have to do integration by parts. And now we're like, okay, but what's our u's, what's our v's, how do we even do this? Well, we want our u to be something that slowly goes away or entirely goes away as we take its derivative, and we want our v to be something that we know that's very easy to integrate. So with that being said, well, we're going to set our u equal to x. That would mean du, so the derivative of x, is just going to be, du is going to be, well, just 1 times dx, right? Because du dx is equal to 1, and then you just bring over this dx and say, well, du is equal to 1 dx, which is just equal to dx. And that's very easy to work with. And then with that we can be like, okay, so then our dv has to be sine of x dx, And our v, well then, we just have to find the integral of sine x, which is just going to be equal to negative cosine x. And so now we've established what our u, du, dv, and v are, and so we can just plug it into the formula. Well, this integral x sine x dx is equal to uv minus the integral of v du. So this is just equal to x sine x minus, well, the integral of v, so negative cosine, so negative cosine with a minus, we'll just make that a plus initially, integral of cosine du, well, du is just dx, so then that's really easy. So then we know, well, we know the integral of cosine, so then we can just say the integral of x sine x dx is just going to be equal to x sine x plus sine x. And then we always have to have that plus c because this is an indefinite integral. We never know. There may be a constant that we add on at the end that goes away when we do the differentiation. So this is one example. Now, what if we had bounds? Because the last time we had an indefinite integral, we had to always put that plus c, and now what if we want to actually find an area that gives us a number, not a function? Well, we just do the same thing and we add bounds to our integral. We know how to do this. So then this is just, well, f of x, g of x, from a to b, where we plug in our numbers, minus, well, the integral from a to b of, well, it's uv minus v du, so then that would just be g of x times f prime of x dx. And so we just, boom, add bounds, easy money. We know how to do that. And so now let's do an example. What if we wanted to find the integral from 1 to 3 of ln of x dx? And now we think, okay, integral of ln of x. We know that, right? It's 1 over x. No, it's not. We know that the derivative of ln of x is 1 over x, but we've never actually seen the integral of ln of x before. So, how do we do it? Well, I see one function here. I see ln of x. Actually, I see two functions. I see this is equal to the integral from 1 to 3 of ln of x times 1 dx. And now, that should give us a hint as to what our u and our v should be. Well, we are going to take our u to be equal to ln of x, and then that would mean our du is going to be equal to 1 over x dx over x dx, and then that would mean our v is going to be, or our dv is going to be equal to 1 dx, which is just dx. So then dv is equal to dx, which would imply, or mean, that our v is just going to be equal to x. So then we can say, well, this, the integral from 1 to 3 of ln of x dx, is just going to be equal to, well, uv, so x ln of x, because I didn't want to write ln of x times x, that's ugly to look at, minus the integral from 1 to 3, and we have to include our bounds, 1 to 3, and then minus, and that should be 3, well, minus v du, so that's going to be equal to x over x dx, which is just going to be equal to 1 dx, which we know, this very well, is just going to be equal to x ln x from 1 to 3 minus, well, that's just going to be x from 1 to 3. And so, because the integral of 1 is x, and we know that very well. Come on now, Logan, why are you even saying this? So then we just plug in our bounds and we can say, well, this is just equal to 3 ln 3 minus 1 ln 1 minus 3 plus 1, right? Because, boom, that's negative, so then the negative 3. And then we can be like, well, ln of 1 is 0. We have 3 ln 3 minus 0 minus 3 plus 1. So then that's just equal to 3 ln 3 plus, nope, minus 2. And that is going to be how we actually find the integral of ln of x, because we've never seen it before. So now it brings up the question, how do we even know what our u's and our dv's should be in the first place? Well, I had mentioned earlier that we want our u's to go away if possible, and we want our dv's to be very easy to integrate. So we want our u's to go away because when we take derivatives of u, it slowly gets smaller and smaller, maybe if we had a polynomial or something. And then we want something that's easy to integrate for dv because we have to find its antiderivative. So we follow this technique. It's called liat. And notice that I said technique, not a rule. Liat does not always work, but we can use it most of the time. And then if we notice, okay, this is not working, you should just switch what you use for du, or for u and dv. So what is liat? Well, liat is logs, inverse trig functions, algebraic expressions, and then trig functions, and then exponential functions. And this should make sense, right? Logs we really don't know how to integrate. I mean, we just learned how to do ln of x, but we know how to differentiate them super easily. Inverse trig functions, those look horrible to integrate, but we know how to do the differentiation quite well. Algebraic functions are right in the middle. They're as easy to integrate as they are to differentiate. And then trig functions, we can differentiate them, but they're also super easy to integrate, so why not have it? And then easiest of all, exponential functions to integrate because, well, we know the derivative of e to the x is e to the x, and we know the integral of e to the x is e to the x. So, as I said, this does not always work. Sometimes we have to do trig functions above our inverse trig functions above our logs. Sometimes we'll have something different. But start with this strategy, and then if it doesn't work, then just swap them. Because this strategy will work 88.7% of the time. So let's do one more practice question, and let's transition to a homework problem. So we're going to just do one question because this video is already getting kind of long. And we're going to do number 31 from our book, the integral from 1 to 5 of m over e to the m dm. And so we can also just rewrite this, if it's helpful, as the integral of 1 to 5 of m times e to the negative m dm, capital M. And so we look at it and we're like, so how should we do this? Well, let's do liat on this thing. And we are going to see, okay, well, we have an algebraic, we have a polynomial, well, a linear function, which is a polynomial, and then we have an exponential function. So we always want to take our exponential functions to be our dv's, so then that means this m is going to be stuck with a u. And then that makes it really easy. So this is going to be our u, this is going to be our dv, and it is important that we include this, the dm, because we have to integrate and we have to have what variable we're integrating based off of. And so that's important to carry that. But so we have that u is equal to m. So then du, well, that's really easy to calculate, is equal to 1 dm, or just dm. And then, well, from there it's really easy because we already found our u, so we have our dv by just process of elimination. So then we have our dv is going to be equal e to the negative m dm, capital M. It's important to have our notation correct. And then we say, well, v. Well, what is the antiderivative of e to the negative m? Well, the antiderivative of e to the m is e to the m, but we have this negative, so then our integral, our antiderivative of e to the negative m is going to be negative e to the negative m. And so now we can just do the integration super easily. because we have our integration by parts formula. So we can say, well, this integral, this 1 to 5, m over e to the m dm is going to be equal, capital M, is equal to uv, so m times negative e to the negative m minus the integral of v du, which is just dm as our du. So then that would just be negative e to the negative m. So we're going to say, okay, that becomes positive. That's e to the negative m times 1, which I'm not even going to write. I'm going to say, but I'm not even going to write, times 1 dm. And so then we can just continue a little farther. And I forgot to write our bounds, so we have to do bounds 1 to 5 and 1 to 5. And then we can say, well, this is just equal to negative m over e to the m plus, well, what is the integral of e to the negative m? dm. We know it. It's negative e to the negative m. So then that's just minus e to the negative m, which is also equal to 1 over e to the m. And this is from 1 to 5. So then we plug in 5 and we get this is equal to 5 over, and we can just do this, we can group these and say that's 1 to 5. So then that's negative 5 over e to the 5 minus 1 over e nope, that's a plus e, and then that's a minus 1 over e to the 5th plus 1 over e, and then we can just group all these together. Well, we have a negative 5 over e to the 5, and then we have a negative 1 over e to the 5, and then we have two 1 over e's, and we can just rewrite this as, well, this is just going to be equal to negative 6 plus 2, or negative 6 over e to the 5 plus 2 over e. And that is going to be our answer for finding the integral from 1 to 5 of m over e to the m dm. So that is all I wanted to cover in today's video. There will be homework, suggested homework, posted down below, just a few problems that I think are really good to practice for integration by parts. As always, my name was Logan. Thanks for watching. Have a great day. So now comes the... I need a sip of your yerba mate.